We've studied the issues of vanishing and exploding gradients in neural networks. RNNs are especially prone to them. Why is that the case? And what are two ways which are unique to RNNs to mitigate vanishing and exploding gradients? Recurrent neural networks allow us to learn the past. It finds patterns in past sequences and uses it to predict the future. If you build an RNN to learn the recent past, here is a function representation which connects the inputs to the RNN with the output. The output at time instance t, that is y of t, is a function of x that is fed in at this time instance, and y of t minus 1 and y of t minus 2. This particular RNN is only focused on the recent past, in fact, on the last two time instances. We unroll the RNN through time, and this helps us learn the past. And the recent past, you'll find out, is no problem at all with regular RNNs. You'll unroll the memory cell through time to form the layers of the neural network. Here, every layer is a memory cell, and you can specify any number of neurons for that memory cell. That is a part of your hyperparameter tuning. Remember, this is the same memory cell at different time instances which make up the RNN layers. Now, recurrent neural networks are trained via a tweaked version of the backpropagation algorithm, and that is called backpropagation through time. The algorithm itself is very similar to backpropagation. However, you'll find that there are a few extra details that we have to worry about as we unroll the layers through time. Now, the number of layers that we have in our recurrent neural network depends on how many time periods we want to process. For a single time period, we need a single layer. Because RNNs work very well with time series data, it's often the case that you'll have problem statements where you want to look very far back in time for patterns which affect the present. This is when you learn the distant past. In the formula represented here, notice that y of t depends on the output 1000 time instance in the past. This means that your unrolled recurrent neural network will be 1,000 layers deep. And when you train such a deep neural network with so many layers, it exacerbates all the problems that you had when you trained regular neural networks that were far shallower. The gradient from the output has to be propagated back a very, very long way. Because recurrent neural networks can be deep, they may be unrolled very far back in time to learn sequences that occurred a long time ago. Those sequences might be very relevant for problems or predictions that you want to make now. This makes RNNs especially prone to vanishing and exploding gradients because gradients have to be propagated back through all of those layers. We studied this problem in some detail when we first looked at neural networks. You know that to cope with vanishing and exploding gradients, there are several things that you can do to mitigate this problem when you're training neural networks. The first is proper initialization. You'll use Xavier and He initialization or other kinds of initializations to randomly set up the weights and biases before you start training your neural network. We've also studied how important the choice of activation function is in the design of our neural network. If you choose non saturating activation functions, such as the LU or the exponential linear unit, that goes a long way in dealing with this gradient problem. Batch normalization is also another common technique to deal with this problem. This is where you center the output of every neuron around zero. This you do by subtracting the mean and dividing by the standard deviation or the variance of the outputs. Or you could use gradient clipping, where you clamp your gradient values to some maximum or minimum and you don't allow them to explode. When you're working with recurrent neural networks as opposed to just regular neural networks, you'll find that if your output relies on the distant past, vanishing and exploding gradients are very likely indeed. So, you have some other techniques that you can use to cope with this issue. One option is the truncated BPTT, that is the truncated back propagation through time. This option exists, but it's not really ideal. Turns out it's a rather simplistic approach Just discard the distant past and only hold the recent sequence in order to make your predictions with the recurrent neural network. Now, this isn't great because what if you have patterns in long term data that you want to include? With truncated BPTT, that's not possible. What we'd really like is for some way that our recurrent neuron could store long term state, some way by which events from the distant past could be recorded in our memory cell. And for recurrent neural networks to be practically applicable in the real world, this is what data scientists have been working towards: a way to store long term memory and state within the recurrent neurons so that vanishing and exploding gradients can be mitigated. It was research into this problem that gave rise to LSTM, or the long short term memory cell. We'll see a demo of how basic recurrent neural networks work first before we go on and study this LSTM cell. It's often the case that you want to use recurrent neural networks to learn the distant past. When you go very far back into the past, the recurrent neural network will end up having many layers and be very, very deep. Such recurrent neural networks are harder to train and are more prone to vanishing and exploding gradients. That's because gradients have to be propagated backwards from the output layer to the input layer a very long way. The deeper the neural network, the more likely it is to have issues with vanishing and exploding gradients. In addition to all the usual ways in which you'll deal with vanishing and exploding gradients in neural networks, such as batch normalization, non saturating activation functions, gradient clipping, and so on, in RNNs, there are two additional ways that you can use. One is truncated backpropagation through time. Here, you won't use all events from the distant past, you'll only use a subset of these events. Another way is to store more state within your RNN memory cell. This is called long term memory. The more state you store, the less prone your RNN will be to vanishing and exploding gradients.